I figured I'd start this video with a couple examples, just applying some terminology from the previous videos. Like this story, my mom tried to teach our goats to pee in one certain spot by giving them treats when they'd pee in that spot, except that they think that now whenever they pee, they get a treat. So whenever they see my mom, they pee. So oops, mom has accidentally become a discriminative stimulus, setting the occasion for peeing, because she was a stimulus that was present during that contingency in the past of pee leads to treat that they were learning. And this Dairy Queen sign, scream until daddy stops the car. Like, it's great advertising, right? But also think about what might happen here. If the kids in the car follow these instructions and dad gives in and goes to Dairy Queen to shut them up, that screaming behavior is likely being positively reinforced. Something yummy is added when they do the screaming behavior. So in the future, when driving past Dairy Queen, they're likely to do that screaming behavior again. All right. Anyway, let's move on to the current video, which is going to be a short one, just covering some basic procedures for operant conditioning and some relevant terms to go with those procedures. So first off, a ton of basic research in the experimental analysis of behavior has traditionally been done in an operant chamber, sometimes called a Skinner box after B.F. Skinner. It's basically a box of whatever size we choose, right? It depends on, the animal you put in there, but it gives an environment where we can present or remove whatever stimuli we want in a very well-controlled manner. So commonly it'll have things like lights inside of it, perhaps of various colors, and usually a way of making sound, like playing tones or music or something. There'll usually be a way to pop in some food or treats to serve as reinforcers for behaviors we want to increase. So that's what they mean by food magazine here. The food magazine is like the little food dispenser goes into this little thing they can eat out of. And the sides of the chamber are often transparent, so we can observe the animal's behavior. This is especially important if we want to set up some sort of contingency, like we'll only give it food if it scratches its butt, or we'll only give it food if it scratches its butt when the green light is on. But we have to see whether they're doing the butt scratching behavior, so we have transparent walls. Or sometimes nowadays we might use a hidden camera. But of course, it's a pain in the ass to have an experimenter watching the rat the entire time, possibly for an hour or longer, and that person has to press the food reward button every time the rat does the behavior they're watching for, and ideally rewarding it immediately with no delay and never missing it once despite being human. That's not ideal. So, to provide an even more sort of tightly controlled experience, we might instead study operant conditioning principles by sticking to a very simple behavior that's super easy for the box itself to measure, and then the rewarding can be automated by the operant chamber. So you'll often see operant chambers have like a lever inside that the rat can press. That would be the behavior that we're targeting, and the food might be contingent on lever pressing behavior. Or if it's a different species, like if it's a pigeon in one of these boxes, you might see a button that can be pecked for the behavior. So we can set up contingencies like button pecking behavior leads to food and do it in a nice automated way where the operant chamber itself does the training for us. So here's an example of a pigeon in a Skinner box in one of these operant chambers.
Can pigeons read? This one gives every indication, because he's been taught to distinguish between two words and to behave appropriately. He's learned his different response to each sign by being rewarded with food. So the bird isn't acting independently. Its behavior is shaped by controlling its environment. The first task was to isolate an individual piece of behavior and see how that could be changed. Skinner did this by keeping individual pigeons at about 3/4 of their normal weight, so that the birds were always hungry, and food could be used as an automatic reward. The pigeon was studied in a uniform box, one it quickly grew used to. One piece of behavior, pecking a coloured disc, was measured on a graph. pigeon learned that pecking the disc produced a reward. Then the behavior of pecking could be studied in relation to how often that reward was offered.
So they mentioned keeping the pigeons at lower than their free-feeding weight, which is called food deprivation. Food deprivation is an establishing operation. It's a motivator to make sure food acts as a reinforcer for the pigeon. Remember that motivational operations, they change how well a reinforcer works, in addition to making the behavior more or less likely to happen. So basically, this is a procedural trick a researcher could use to make the operant box setup work better or faster for learning. Now, as an aside, when they say the pigeons were kept below their free-feeding weight, it's not as bad as it might sound to you. The animals aren't being starved at all. Their free-feeding weight would be the unrealistic scenario of unlimited food. In other words, they might even get a little chunky if you give them all the food they can eat. So food deprivation in a lab often means they're ending up at a weight that's similar to the weight in the wild, which leaves them motivated to find food reinforcing in a way that, it wouldn't be if they were already full from an all-you-can-eat buffet. Meanwhile, just to apply some of the terminology we've learned to this video here, we can see that the peck versus the turn signs in that little box, those were discriminative stimuli. So peck is a signal, we could say our first discriminative stimulus, that says pecking will lead to food. So the first behavior of pecking, R1, will lead to food. If they do R2 when the peck signal is up, if they do the turning behavior, then it doesn't lead to food. So the peck signal sets the occasion for the pecking behavior, making pecking more likely. The turn sign, that's a signal, a discriminative stimulus, the second one, that says turning, our second behavior, will lead to food. So it sets the occasion for turning, making that more likely, but if R1, the first behavior, shows up during that sign, nothing happens. So the pigeon's behavior, pecking or turning, is affected by whatever discriminative stimulus happens to be present. Now here's another example, this time of a rat in a Skinner box. You'll notice when the light is on, the light is a discriminative stimulus that sets the occasion for lever pressing behavior. In other words, the light, the SD, signals that the contingency, R leading to SR, behavior leading to reinforcer, that contingency is active. Pressing the lever will produce food. So that's what a simple Skinner box setup might be. Here's a slightly more complex Skinner box setup. So there's a lot of different ways these can look depending on what you're trying to train or what you're trying to test. Other versions may include various colors or sounds. Sometimes if they're studying, unenjoyable, aversive stimuli that the rat doesn't like, they might add a little electrical shock to the floor that they can turn on. Generally something that's, mildly annoying, not something that genuinely hurts. But there might be a series of lights or special timing set up with the lights. A lot of different varieties. Can be kind of complex. All right, and then this last clip here of an operant chamber is actually going to show that shaping process that we talked about before. So in this case, how do you actually train a rat to press a lever in an operant chamber? How do you get them to start pressing the lever for food, after which you can test whatever you want to test? So as you'll see in this video, shaping is basically a way to sort of capture a behavior that they might do just accidentally the first few times. So here the rat's just kind of getting used to the chamber when you put it in first, but how do you get it to start doing the behavior of pressing the lever? You got to first just capture some of those intermediate behaviors, little steps toward what you want. So, accidentally once in a while it might turn towards that direction. That causes the food to show up. They might not realize their behavior is causing the food to show up, but the brain will start to pick up on that pattern. Pretty soon they'll start to hang out closer to the lever, explore more near it, kind of vary their behavior until it happens to work again, and their brain will notice what behavior was happening right before the food showed up, which is enough for operant conditioning to start kicking in. So eventually they'll be doing the target behavior we want of, pressing the lever at a fairly steady state at, whatever rate they cap out at. So now the rat kind of knows what it needs to do. In this new contingency, it has to actually touch lever. And now we get to the sort of last step. It has to actually press the lever down, not just touch it. So that's shaping in action, and you can see how we can use that in an operant chamber to get a rat doing a behavior that it might not normally do a lot. But now we can start studying things like behavioral rates when we change other things about the environment. So the lever pressing behavior becomes sort of a dependent variable, and we can start to change various independent variables, whatever we want to study. And we've created this nice experimental setup with a lot of control where we can study behavior in a very basic way. So you can think of the most basic procedure for an operant conditioning study as something like this usually. You first would want to find the baseline level of the behavior where you're not reinforcing it at all. Sometimes we call this the operant level. It's just how much they do the behavior before your learning starts, before you set up the contingency. Then you set up the contingency, some behavior leading to a reinforcer. And if you set it up so that, let's say, every single time they do the behavior, they get a reinforcer, if they're reinforced every time, we actually have a term for that. We call it a CRF schedule, and that's short for a continuous reinforcement schedule. We'll come back to this, and we'll talk about some alternatives to that in the next big topic, but meanwhile, for the basic kind of research study that we're going to talk about, you would basically just record how often the behavior occurs when that contingency is active. And you're comparing that to the baseline level of the behavior, to the operant level you recorded first. So you're seeing the difference in the behavior when you've changed this thing about the environment. In other words, when you've turned on some sort of contingency. And most of the decades of research done in the experimental analysis of behavior is some variant, often some complicated twist on this basic kind of procedure. So how do we record how often the behavior occurs? Obviously, we could tally it up by hand, but that's not only a pain in the ass, it would actually lose a lot of important information like the timing of how much time passed between each instance of the behavior. So generally, we automate the recording of the behavior. Nowadays, using a computer, obviously. And what we create is called a cumulative record. It's a graph keeping a record of exactly when each response occurred. And we can see, the cumulative amount of total behaviors that have occurred from beginning to end of the study. So this tells us, by looking at it visually, it'll tell us the rate of the behavior, like the number of behaviors over a certain amount of time. So we can see how that rate changes in different circumstances. Since it's the rate of an operant behavior, it's called the operant rate. Just means that the rate of the behavior we're measuring. Okay, so that's the term operant rate. Just means how often they're doing it. The rate is sort of the most basic kind of thing we like to measure in these sort of studies. Now, even prior to computers, they came up with some clever ways to automate making a cumulative record with something like a Skinner box. So for example, they would set up a big roll of paper and it would roll out at a constant rate over time. And there was a little pin pressing down on it. So as time passes and the paper rolls along underneath the pin, it creates a straight line, right? But then they hooked it up to the lever so that every time the rat did the lever pressing behavior, it actually moves the pin up just a slight bit. So on the graph that's created, every time it moves up a little bit, that means a behavior occurred right there at that point in time. We end up with the x-axis being time, and then the y-axis being the cumulative number of behaviors that have happened so far. And it all gets graphed out automatically on this long roll of paper, even before computers existed. It's nice because it gives a visual depiction of when and how often and how quickly the behavior occurred. You see basically the whole history of this animal's behavior in a single graph. So specifically when we look at the graph as a whole, what we're often interested in is the slope of the graph. The slope at any point indicates the operant rate, the rate of behavior over a given amount of time. The steeper this slope is, that means the faster the behavior is happening there, and the flatter the slope, the less often the behavior was occurring. Now, another important part of a cumulative record is keeping track of when reinforcement was delivered, like when did the treats go out, so that we can deduce the relationship between reinforcement and how that affects behavior. So again, this is automated. So For example, when the food magazine pops out a piece of food, the operant chamber might also force the pen to bounce in place, just a little bounce that creates a little tick mark on the cumulative record. So on a cumulative record graph like this, reinforcement is marked with a little tick mark. If we're using CRF, continuous reinforcement, then there will be a tick mark every time the response happens. But maybe if we're only reinforcing every 50 responses, like in the graph up here, they only get the reward every time they press the lever 50 times. Then the tick mark tells us when they reach 50, when they reach 100, when they reach 150, and so on. And we can look for interesting patterns in their responding. Like, notice here, sometimes the slope is pretty steep, meaning a lot of responses all in a row at a constant rate. But in other times, at other parts of this graph, like right after they get food, notice that it's totally flat. So that means they're not responding during those times, or responding at a very low rate. So those are interesting patterns we might notice across creatures or across species, and thus need to figure out why that happens. We can see it all happening there in the graph. So here's some example data from an actual real life study done with bees. So on the left here, we've got the data from the appropriately named subject B3. Compare that to the data on the right for a different bee, the subject B9. B3 here on the left is responding at a much higher rate, much faster than B9. So for example, B3 reaches 120 responses, right? The cumulative number, it's got up to a total of 120 responses after about 2.5 minutes, right? 150 seconds. But subject B9 hasn't done 120 behaviors until much more time has passed, about 6 minutes, right? 350 seconds. So the graph holds quick bits of information, or quite a bit of information, that we can also compare quickly and easily since it's visual. B3 did roughly 120 responses in 150 seconds and got how many? 9 reinforcers. Just by counting up those tick marks, we can see how much food B3 got. What about B9? Did, roughly 50 responses in that same time frame of 150 seconds. So that's way fewer responses, and only got 4 reinforcers in that time frame. But then it took 350 seconds to get all the way up to 120 behaviors. So we might then ask, why? Why did one bee respond so much faster than the other? Presumably, what happened here is we set up a contingency differently for these two bees, and we're testing how it affects behavior. So don't worry about the details right now, but the little 0, 15x and 0, 30x up top, that's telling us something about the experimental condition each bee was assigned to. They set up the contingency in a certain way for each bee. That's sort of the independent variable, and we're looking at their behavior here, which would be the dependent variable. And we will get into all sorts of experiments like that in the upcoming videos, but for now, you just need to understand that this is the power of an operant chamber and of recording, making something like a cumulative record. We have tight control over all the variables in the experiment, and that lets us make kind of solid comparisons between different conditions or different contingencies we might want to set up, and see how changing those conditions or contingencies affects the operant rate, affects the rate of behavior for the things we're testing. And that's how we can learn some very basic principles about how behavior works, maybe even universal principles across all creatures. Now, one last side note before we end this video. Continuous reinforcement, the CRF schedule, is not always the best setup for learning. It's not what we always use. And there are a few reasons why CRF might not be ideal sometimes. So first off, using food reinforcers every time that they did the behavior would make the recipient unhealthy, right? Especially if the training involves thousands of trials, you're going to end up with a really fat little rat or pigeon or whatever. Also, in other circumstances, it's not ideal because it's potentially really expensive. Like if you give your kid, as positive reinforcement, you give your kid a new Lego set for every homework assignment they complete, you would go broke in a month. And more fundamentally, it's not always possible to do CRF. Like, you can't be there to give an M&M every time your child says thank you, because sometimes you're just not around. And as we'll see, it turns out the science very clearly shows that reinforcing less often, what we'll call intermittent reinforcement can sometimes be a more effective way to control the behavior. And it may have other useful properties we want, like maybe it makes it harder for the behavior to go away after our training or something like that. We'll come back to that in the next big topic. But first, for this topic, we'll just have one more little video on extinction. Previously, we learned about extinction in respondent conditioning, but we'll see that the same kind of idea shows up in operant conditioning.